Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's problem we are going to do a square tube crush test. This particular problem is actually a nonlinear buckling with capturing the post buckling behavior. Because you see our couple of videos on the nonlinear buckling side, we are not really capture the post buckling behavior. We capture what is the maximum buckling load, and we are no more interested in the post buckling behavior. But there are the situation where you are interested in the post buckling behavior from the crash energy point of view, energy storage point of view, like automotive cars. When they crash, they have a crumple zone, so you are interested how much is the energy absorption during that buckling event, control buckling event. So this is the particular is a aluminum square tube with 450 millimeter height, and we'll find what is the first buckling mode. Then we'll add imperfection and see how this crush behavior is there. So this problem we are going to try today. Now the motivation for this problem is one of our subscriber asked, when we done nonlinear buckling, can you do buckling in Abaqus Explicit? Yes, we can do in Abaqus Explicit. We can capture the post buckling behavior, and then the methodology is almost similar like what we had done, but a bit twist to this. So there are a lot of problem in this area, so we are going to do this problem now. I will just quickly go through what exactly we are going to do. We are going to do nonlinear buckling in Abaqus Explicit, not in standard. So it will be two crush test, and this is exactly we are going to do. We are going to connecting Abaqus simulation to reality. Lot of problems are there within this domain, where actually you crush the tube, you want to understand how is the post buckling behavior, how is the deform shape. So we are going to capture the same thing here. So you see this, the fold. So the fold goes the one direction, then fold go to the another direction, then it's gone. And similarly we can capture in Abaqus. Now how to capture that? You have to include imperfection. You do some imperfection study, and we can always get the capture the what is the deformation mode, and then we can capture the force. How is the force over a period of time, that's over a period of displacement, that will capture. So if you remember, we have captured this point, we are not gone beyond this point. If you want to really go and capture the post buckling behavior, so I'll just go back one slide. So if you see, so you have snap through behavior. So this buckle, the two folds come in contact, again it picks up the load, then that get buckled, then it gets snap through behavior, then again load get pick up, then it goes to snap through behavior, and then it's come to the end. So this snap through behavior of buckling, that's what we're going to capture. Now for that, you cannot really capture with arc line method, because arc line method have some limitation, contact have some limitation in Abaqus standard. So we are going to capture this in Abaqus Explicit as a quasi-static analysis. So this is the exact problem we are going to do. Now quickly going to the methodology. What we are going to do, we are going to do a first linear buckling. We'll add a node fill file which will capture the displacement. We'll have a first 3 mode. You can have number of multiple mode. This eigen mode and eigen values we are we are mainly interested in eigen mode, deform shape. So that deform shape will add imperfection when you do a nonlinear buckling in Abaqus Explicit. We are going to do in Explicit for a 200 millisecond. We are going to pull it down by 250 millisecond, 250 millimeter, and then with this imperfection we'll capture node history output, and then we'll plot how is the deform shape. So quickly going through problem, it's 100 millimeter by 100 millimeter, 450 millimeter in length, 2 millimeter. Aluminum properties, typical aluminum property. We also have plasticity data, fixed condition, pin condition, and we're going to push this by 250 millimeter. First we'll do linear buckling, eigenvalue deformation, will add imperfection, then we'll do Abaqus Explicit and capture what is a post buckling behavior. Eigenvalue extraction, we are going to use star buckle. We are going to use a subspace because we have minimum number of these modes, and the main motivation is to get a deform shape. So let's one more time. So you have this first buckling, then second buckling mode, then you get a multiple force. So every time when this get connected, your load gets up and then down. So let me clear this and let me set the directory. So we'll first create a column. So deformable shell extrusion we are going to do 200 by 200. So I'm going to put 0 comma 0, then I'll put minus 49 comma minus 49 because we are going to put it on the mid surface, and then I'll put 49 comma 49. So we get two extreme corner. So we have done this. We'll extrude this by 450 millimeters. Then we'll quickly create metal property. It will be aluminum. We are going to put density because we just want this property for Abaqus Explicit analysis. Now first we'll do a linear buckling mode. So after linear buckling, whenever we go for Abaqus Explicit, there where you required a density also, because you are going to do in explicit solver. So let me just check one more so Poisson's ratio is 0.35. I'll add a plasticity 160 is a yield for this aluminum alloy, and 340 it is 30%. I'll also give thickness 2 millimeter, and then we'll just assign this to column. So we have done a column, we define geometry, we are given thickness, we are given metal, everything we are assigned. Now we'll quickly create now one more part. Will be two plates which will be rigid. So I'm going to create bottom plate. It will be discrete rigid. We are going to do in a planar. So shell planar discrete rigid bottom. I'll again put 0 comma 0, then I'll put minus 100 comma 100, then 100 comma 100, and then so we are done this. Only thing is we'll quickly assign the reference point for boundary condition. So I'm going to add a reference point 0 comma 0 comma 0. So I just given reference point in the center. Now similar part we want at the top, so I'm going to just copy it. So it will be top. So I have created the column, I created a bottom, I created a top. Now what we'll do, we'll create a in assembly. So we are done with the assembly, and then I'll just move the top part by 450 millimeters. So 0 comma 0 at the starting point, 0 comma 450. So it just reached top. Now what we are going to do, before meshing, we'll do meshing also, and then we'll put this tie constant here, tie constant, then we'll put fixed condition, and then pin condition, and we'll just apply force. So let's go to the meshing module. Meshing we are going to do in the part. So column, I'm going to select this, and medial axis is what I'm going to use for this. Global length 5, and then element will be S4R. It will be standard, but then later on we'll shift to the explicit one. And so you give standard, linear, give S4. When you go to explicit, then we'll also hourglass control will go to enhance hourglass, but that is when we do explicit one. So we mesh that, then we'll take a bottom one which will be like 10, and it will be standard R3D4. Then we'll create top, again 10, So now if you see, you have done meshing. Now what we'll do, the node set column bottom and the top node set will create a set, so it will be easy for us to give a tie connection. So I'm going to go to the set, create. I'll put this in this nodes. It will be bottom nodes, and then similarly we'll have a top node. So I'll say bot nodes. Some issue, then let me create it. Create node set bot, and then let me individually select it. So let me also put in this view, and let's see whether all is selected. It's not selected all, so let's zoom it properly and do it, because this is important. We need to put a tie connection there. So it's selected, done. I'll create one more set for nodes at the top. I'll zoom it, and then we'll have individual selection. So we have done that. So this is important for the tie connection. Now we'll go to so with DN assembly we are not created the step. Interaction will go, we'll create tie. It will be first bottom tie, and then the master surface is this one. So I click and then surface, done. Now there is no condition for normal for tie, but I just follow. So the brown is S pos, so I selected the pos side, so surface will be at the top side. So we selected the brown. Node region, I'm going to select from the set, we'll say highlight, and then this is important, guys. So you specify the, I just specify 5, so whatever the closest node between the 5 will get tie. Adjust slave surface initial position, I just say no, because other, if you put this is equal to condition yes, then it will pull this node on this surface, so I put no. So that way there will be no distortion of element. So you connected there. You'll create one more at top. So you select surface, you select this. So we want a below surface, so the bottom side. So top is brown, so we selected the purple, and the slave surface will select from the nodal region top, and then I'll specify distance like 5, so it can get whatever all closest node tie. Adjust slave initial I'll not put, and then this is done. Now we'll just put a boundary condition. Bottom will be end caster. So you select the reference point, done. End caster, we are done. And then top, it will be pin condition. So let me first create it again. So I selected the wrong, I select the symmetry antecedent. You have to select the displacement and rotation, and then you select this, the reference point, and you put X and Y constant, you keep it vertical as free. Then we'll just create a step. It will be linear buckling first, then you go to linear protrusion, you go to buckling 3 we are going to say, and I just put 300 iteration just to get there should not be any issue. I think 100 will be more enough, but we have put 300 iteration, and then we'll just apply a load. It will just unit load we are going to apply it on this reference point -1, and then let me save this as linear buckling. We'll create a job quickly. We'll put a data check. I just opened in a text pad. So we have just looked into input file. We'll just add a node fill output here because I'll just go to the PowerPoint presentation. So we define, we'll add a node fill file which will have a displacement plot here. Now I already copied the command in separate text file, so I'll just add it that before the end step. So that linear buckling file will be ready. You can add this using edit keyword option. Also you can add node fill here, but I just prefer from the text pad. So we'll quickly from command prompt, I'll give a run. ABQ6145, that is my version. Your version may be different. And then I'll just copy this INP file. Interactive. So let's check what is a buckling mode we got. So we just submitted the pre-done. So this will quickly done. So I think we'll just wait. So once we get this IGN mode, this deformation we are going to take in a nonlinear buckling. So nonlinear buckling we are going to do dynamic explicit. We'll just give a add this imperfection in that. We'll define a contact also, automatic general contact, and we'll just try to push it down. That's what exactly we are going to do. So let's see where it is gone. It is just completed, so we can just check results from here. So let me put this state on, and then sorry, state on. So now what you see, the first mode is around 93, first one is 92, second is 93, and then third is like 100k, 105k. So this all deformation mode, what we are going to do, this deformation will just add in imperfection. Now what we'll do, first we'll just delete this job. So first we have done a linear buckling, now we'll do a non-linear buckling. So steps, I'll go, I don't want this, delete it, I'll delete it. Our new steps will be, first we'll define a contact. So we are going to do Abaqus Explicit, so the part is going to come in contact. So first define the friction. Tangential behavior, penalty base 0.3 as a friction, and then we'll define automatic general contact. So general contact explicit, we are going to add friction. We are done. So we're done, define a contact. Now we'll quickly generate a step. This will be non-linear buckling. This will be using dynamic explicit. So time period will be 200 milliseconds or 0.2 second. On, we are not doing mask scaling because already we have done quite a 5 millimeter mesh. Now what we'll do, we'll just add one more boundary condition. We have fixed pin, and then we are going to pull it down. So create pull down displacement we are going to give. We'll select that point, and then we'll say minus 250. We are going to give a tabular form, like 0 time we have 0 displacement, and 200 millisecond we have full displacement applied, and we'll connect it here. So we are given this. Now only thing is we are going to put a force for the displacement. So for history output, we are going to add in history output. First let me create this for the top plate. We'll create one set is a top RF where we are going to measure reaction force. So we selected that, and then we'll create a history. We are going to generate for specific node that this will be like for every 0.0001 second. But what we are going to develop. So we are going to have a displacement, so U3 displacement, and then we'll have a reaction force. So you see U3 and RF we are done. Now we'll quickly create a job, nonlinear buckling, put on a data check. So once data check is done, we can just do add imperfection in that, and then we can submit a run. So just submitted, pre-processor done successfully. So I think there is no issue, so we can just go there. And so let me save this file also, nonlinear buckling CI. Then you go to, I just open this in text pad, control N, then you have all contact defined, boundary condition, you are given prescribed displacement. We'll just add this imperfection. Now imperfection sensitivity study you have to do, guys, before adding imperfection. I've done this for this model, but for your model also you have to see. So we are giving a same imperfection like 0.2 for all three modes. So all three modes displacement are important to add the imperfection. So all three mode we are given, and its linear buckling is the file. Just a minute. I think I added in the wrong file. So we open a nonlinear buckling file, and here we are going to, before the step we are going to add the imperfection. We are given a same imperfection importance to all three modes, and your T50, then your contact, you are given friction. So we have this, so we are going to run this file now. abq6145j is equal to, I just copy the name. I'm going to run with 4 CPU. So let it run. So run just started. We'll just wait till we get the results, and then we can discuss on the results. So job is just completed. So let's check into results. So if you look, so you created all the folds and then you can see the post buckling also we are able to capture. So you get buckled, and then now quickly we'll do one thing. Quickly we'll plot force versus displacement, and then check how the post buckling behavior we are able to capture. So if we go to XY creator data, go to the history output, and then we are going to plot reaction force and then displacement u3. So since it was a negative z, so you see the negative z displacement and then you see the reaction force as a negative. So we are going to multiply the force by -1 and this by -1, and we'll plot force versus displacement. So we'll go to xy plot, operation by xy data. We are going to do combine, so it is like -1 then multiply by displacement. So I'm going to take temp2, I'm going to add to expression, then I'm put a comma, then -1 star, and then I'm going to add this in expression and then plot the expression. So if you see, it's 100k was the buckling force for a linear buckling analysis, but for nonlinear it is like a 60. So let's make this axis bigger. The text should be readable. Title also will make it 24. And then you see it's buckle, then after buckling it get connected to the bottom surface, then you pick up the force, then you get a second fold, then it connect to the bottom surface, it's pick up. So that's how actually the fold is generated. So once you plot it, so this was a quick exercise on how to do nonlinear buckling in Abaqus Explicit. Can crush, you can also match some of this deformed shape like this. You also plot force versus displacement, so we are able to capture all this snap through behavior. That is important thing. So guys, if you like this video, don't forget to like us and subscribe us. Thanks for watching this video. Thank you. Bye bye.